Well, there are many pitfalls in which you can fall when you do system identification. We have just seen that if your data is not informative enough, you'll end up with a bad model. Another pitfall is to choose TS, the sampling period, too small, and this will lead to over sampling. Okay, we've seen in the previous slide that TS should be such that there are, well, 10 to 15 samples per rise time. There is also another pitfall that is related to the number of parameters in the model, right? If the number of parameters is taken too high, well, we'll end up with a phenomenon that is called overfitting. This is really an important problem, and this is why I have chosen to discuss this problem in the introduction, so that you would understand the problem before you start the system identification laboratory. So I will explain this problem of overfitting in the case of a static system, a static relation. But this problem is also present if you take a dynamic model and you increase the number of parameters. So in this case, the actual relation is static and it's quadratic, and it's shown here in green. So the actual relation is y is equal to x squared. So here you have the input axis x, and here you have the output axis, and these are the y's. And what happens is that you use your system to do experimentation. You use inputs in the range from -5 to 5, and you apply them to the system and you measure the output. The problem is that there is measurement noise. So this explains that the experiments are given here, and they are represented using these black circles, right? So the idea is to use the data in order to identify the relation between input and output, and for that we'll use a prediction, a model that is of the type y hat, and it's a polynomial function of the input a0 plus a1x plus a2x squared plus up to an x to the power n. So what we'll do is use an identification cost, okay, which is the sum over all experiments of y minus the prediction squared, right? And what we'll do is minimize the identification cost over a0 up to an. And this is going to give us an optimal identification cost. And you will probably have noticed that this is a least squares problem. So this is something that you know, and you should be able to implement it because you have had a course on linear algebra. So you can see that, well, if n increases, the optimal identification cost will go down. Actually, if you use n is equal to the number of data points minus 1, then the optimal identification cost will be 0, because you will have identified a polynomial that will go through all the experiments, okay? But you can see here by looking at this model that even if the identification cost goes down, the optimal identification cost goes down when n increases, this does not mean that the underlying model is capable of representing the actual, well, quadratic static relation. Okay, so what is happening here is that if n is increasing, well, the model is kind of sticking to the noise. So there is a trade-off here. N needs to be sufficiently large for a low bias, okay, but it cannot be too high, otherwise we'll have overfitting to the noise. So choosing n too large is really leading to overfitting to noise, and this is a major problem in some cases. In the next slide we'll see how we can deal with this problem by taking two data sets, one for identification and one for validation. So indeed, you can see here that the data set has been split in two. In red, a data set for identification purposes, and in blue, a data set for validation purposes. Here we have a static non-linear system and the relation is quadratic. Well, in this case you should cover the whole input range. So what has been done is to take every second point for identification and the remaining part of the dataset for validation. So the idea will be to use the dataset in red for identification. So we'll work again with our identification costs, right, which will be the sum, but now only on the data used for identification, of y minus y hat squared, and we'll minimize, well, this cost over the a0 up to an. Okay, and this will lead to an optimal identification cost, and you know that this one is going to go down if n is increasing. But what you will do once you have identified a model for a particular n is compute the so-called validation data cost, and this is the same formula but now applied only on the experimental data used for validation. So we have the same sum but applied on different data. And what you will see here now, if n is increasing, well, the validation cost will go down at first, okay, because if n is growing, the bias is decreasing, and then at some stage, if you increase n, you will see that you start to overfit to the noise and the validation cost will go up, and you'll have a clear indication of what n to choose. So what you see here in red is the optimal identification cost as a function of the number of parameters here. So the number of parameters is actually n, which is the order of the polynomial plus 1. Okay, a second order polynomial will have 3 parameters. And in blue you see the validation cost as explained in the previous slide. And as you can see here, indeed, as the number of parameters increases, this optimal identification cost will continues to go down, whereas the validation cost goes down, and at some stage, well, when you stick to the noise, well, this validation cost goes up, well, slowly here, and you have kind of this knee that is indicative of the number of parameters that you should use. You see here that you should use 3 parameters, and this indeed corresponds to a second order polynomial. And if you have a look at this curve over here, you see that the identified quadratic relation in blue here is very close to the actual quadratic relation in green. Well, this overfitting is related to the so-called bias variance trade-off. If you increase n, of course the bias is going to go down, but at some stage you're going to fit to the noise, and there is a trade-off in choosing n, right? So if the model is too flexible, which means that n is high, then you'll have a very good model in training. This means that the optimal identification cost will be low, but it will be poor in generalization. This means that if you apply the model on data that has not been used for training, for identification, you will have poor results, and this is then leading to a validation cost that is high. So the idea behind preventing overfitting is to check whether the model's predictive performance becomes worse when applied to data that were not used in model estimation. And the idea is to divide the data set in 2 groups, where the size of the identification set is usually a little bit higher than the size of the validation set. Their sizes actually depend on the size of the complete data set. For static models, like in the case that we've just tackled, polynomial models, but also for neural nets, for example, we have to split the identification and the validation data set in such a way that they both span the entire range. This is why 1 data point out of 2 is a good way of choosing the identification dataset and the validation dataset. Of course, and this is very important for dynamic models, you have to choose identification and validation datasets that are constructed from consecutive data points in order not to destroy the time dependence. So it's forbidden to take 1 data point out of 2, okay, because this would clearly destroy the time dependence. The last subsection of this introduction is an example, a practical example, using data that comes from an Hairdryer. The reason that I already present you this example is because very often the system identification lab starts very early before the end of the course. So it could very well be that you do not understand all concepts fully, but please come back to this section, this application section, when you have completed the course. As I've said before, there are other examples that are available using the command docident. So have a look at these examples before you start the identification lab. So you can run this example using the command load dryer 2. This is data that is directly available into MATLAB. And the input here is the power of the heating device, in this case the hairdryer, and the output is the air temperature. So what is done over here is to use a so-called identification data format. It's really an object. So dry here is an object. It has an output, an input, and a sampling period. And then what you can do, you can give a name to the input, to the output. You can give units to time input and output. And the advantage is that later when you make plots, all these things will become automatically available in the plot. So as we have explained just before, you should use data for estimation and data for validation. And in this case, we take the first 300 data points for estimation, and what is done over here in figure 1 is to plot the estimation samples that correspond to the indices 200 to 300. So this is the data plot that you obtain, and as I've said, using this object dry, you can produce with one simple command a plot like this one over here, where you have the input over here. Okay, you have the units of time, you have the units of the input, you have the units of the output, and you have titles. Okay, as you can see in this case, well, the input is a PRBS type signal, and this is the output that has been generated in the experiments. Well, the next thing that is done on the data set is detrending, and detrending is first removing the mean on the input and output, and will remove linear trends. We'll come back to that later on in the course, and then of course the data are plotted. So usually what is done when you start the identification exercise is to start the identification with the estimation of the impulse response of the system. So we assume that the system has a finite impulse response, in the sense that the impulse response goes to 0 after some time. So we directly identify the impulse response. Once you have the impulse response, you can also compute the step response. This is simply a summation of the impulse response elements, right? Later on in the course, we'll see how you can do the estimation of the impulse response, and we'll see that it's basically a least squares type problem. On top of the impulse response and the step response, we'll show the 3 sigma confidence interval. Remember that here we are going to directly identify the impulse response, so it will look something like that. But what you will do also when you do identification is, well, obtain an estimate, for instance, for the impulse response at some time, but you will also obtain, using the identification toolbox, a confidence interval around this estimate. So this is how you can plot the impulse response with its 3 sigma confidence interval. Well, this is the plot after detrending of the data. There isn't much difference with the previous plot. In this case, there was no linear trend to be observed. So what the detrending does really is remove the mean from the input and the output. You can see here, for instance, that the input, well, is varying around 0. So if you use model for simulation purposes, well, detrending can be useful because it has kind of a, well, linearizing effect. Okay, so that you start working around a particular working point, and you'll model actually the variations around that working point. If you use the model for prediction, well, then doing a detrend or not has very little influence on the predictor. So what you have here is the identified impulse response. The input is power, okay, and the output is temperature, power in watt and temperature in degrees. And what you see here below is the identified confidence interval. So if you consider the impulse response at this time, so what you have to do is go and have a look at the confidence interval, and this is, well, the estimated parameter, and well, you know that with a probability of 95%, the actual impulse response at that time will be in this confidence interval. Okay, so this confidence interval tells you how confident you are in the estimate. So what you kind of expect is a confidence interval that is much lower than the estimate itself. So what you see here is that you cannot be very confident in these estimates because they fall in the confidence interval. You have a very small value, right, estimate, and the confidence interval, the sigma value, is much higher. So you might as well say that these three values here are 0, right? So you can see here that you have a delay of 3 samples. TS in this case, if I remember well, was 0.08 seconds. So the delay in the system is of 0.24 seconds. So from the impulse response you can construct the step response. So if you want, for instance, the value of the step response up to this value here, what you have to do is add the impulse response up to this value of time, and if you do that for every value, well, you obtain the following step response. So this is what is obtained using the command step plot. Well, once you have estimated the impulse response of the system, well, you can use it, as we have seen, to estimate the delay. Well, you can go further, and one step further is, for instance, to identify an ARX model, which is good for prediction, and an output error model. And well, this model is often used if you're interested in simulation. And what you can then do is validate the models on a validation set. You can do two things. You can compare the output of the predictors and compare with the actual data, and then you also can do correlation analysis. So for instance, for estimating the ARX model, you can use the command ARX. You will use the estimation data, and this ARX model is based on two polynomials, A and B, and the number of parameters in A is NA, the number of parameters in B is NP, and the third parameter over here is NK, the delay. And we have seen in the example that using the impulse response we could see that a delay of 3 samples is okay. So using this command you obtain an ARX model, and then what you can do is use the command present to have a look at your model. For instance, you will have estimated all parameters in the A polynomial, and for instance you'll have A, and you'll have the value of A, its estimation, let's say 1.37, and you'll have the 3 sigma confidence interval. So for instance, plus minus 0.22, for instance, right? And you have this for every parameter. What I have done for the ARX model, you can do also to estimate an output error method, the commands are very similar, but the model structures are very different. Once you have your model, what you have to do is select a data set for validation, and in this case we have taken the data points with indices ranging from 800 to 900. Since we have done identification with a detrend on the identification data, we have to do a detrend on the validation data. And what you can then do is use your validation data set and compare the output of the predictor when you use model 2, compare it with the output of the predictor when you use model 3, and compare this with the actual data. Model 2 is in the ARX model in red, and the output error model will be shown in cyan. And what you can do also, besides looking at the simulated or predicted outputs, here it is the simulated output, right? If you use the compare method with an additional argument of 1 here, you'll do a comparison between the models and the actual data in prediction. Well, what you can do also is correlation analysis. So what you do is compute the residuals, so that's the output minus the predicted output, and do autocorrelation of epsilon or correlation of epsilon with the input. This is a bit difficult to explain right now, but as I've said, at the end of the course, please come back to this example to, well, see if you understand things. So this is the result of a plot that comes from the compare function of MATLAB, and here we have just used the compare function without any argument, so this means that the prediction horizon is infinite. We'll see that later, and this corresponds to simulation. If you use the compare function and at the end here you put, for instance, an horizon, prediction horizon of 1, you'll compare the models in prediction with a 1 step ahead prediction. So, but in this case there was no argument, so we really compare in simulation. So in black over here you have the actual data, and in red you have the output of the ARX simulator, and in cyan you have the output of the output error simulator. So here is the result of the correlation analysis for the ARX model. Remember that the residual is really the output that is measured minus the predicted or simulated output. It depends, right? So what you can then do is do correlation analysis, and this is really computing R epsilon epsilon tau, where tau is the lag. Okay, and with the notations of the course, and we'll introduce them a little bit later in the course, this is computed as follows. It's a sum of epsilon t, the residual, times epsilon t minus tau, right? And if everything goes well and you have done a good identification, well, the epsilon should be such that, well, it's independent. Okay, so this means that epsilon at time t is independent of epsilon at any other time. So if you use a tau that is different from 0, this correlation here should go to 0, and of course if tau is equal to 0 you sum some squares over here, so obviously you'll have something that will give a contribution. So what you should have in theory, if the model is ideal, is, and this is again the lag over here, is a correlogram. This is how this is called, that looks like this. It's 0 everywhere for every lag except for lag 0, where you have 1 over here. Okay, so we'll come back to that later. What is done here below is compute R epsilon u. So, well, you do a correlation between epsilon and, well, use the inputs. Okay, and again you do this for different lags, and obviously the formula will be 1 over n, a sum of epsilon t ut minus tau. And if your identification has been successful, well, there should be little correlation between the residuals and the inputs. If there is correlation, this means that there is still information in the residuals that can be explained using the input. So if you look at this graph over here, ideally, and this is again lag on the x-axis, you should have something that will look like this. Okay, I say ideally. Why do I say ideally? Well, because in the ideal situation you have no noise and you have an infinite number of data. So in the case of a finite set with noise, well, these values over here will be different from 0, but they will be small. So there exists white nest tests, as they are called, and as long as you see that these values are within the interval here in yellow, you can say that the correlogram is okay. Okay, so this is roughly explaining how you do a correlation analysis. So you can kind of see that, well, the identified model is looking rather well, because as you can see, in for most lags except for lag 0, but this is normal here, well, you see that the correlogram falls inside this interval here in yellow. So we'll come back to that later in the course. So here we have the correlation analysis for the output error model. Okay, it doesn't look too bad for the cross correlation function between the input and the residuals, except maybe in this little zone over here, but the correlation function of the residuals does not look as good as the one that we had obtained for the ARX model. But we will see later in the course that this is kind of logical, because this R epsilon tau, okay, this is this correlation function as a function of the lag, will identify what is called the noise model of the system, and we'll call it h of q. And in the case of an output error model, the noise model that is used is a very crude noise model. Okay, so it's kind of logical that we have problems with the correlation function of the residuals. So what you can do next when you have identified some models is have a look at the pole zero plots of the models. Really identifying these models is really identifying a transfer function. So you have a numerator polynomial and a denominator polynomial, so you can have a look at the zeros and the poles. So again, what you can do is have a look at the confidence interval around the poles and zeros. What can be done next is have a look at the Bode plots of the identified models. And what is nice again is that you can see in the Bode plot the 3 sigma confidence interval region, so that you can know where your Bode diagram has been identified accurately. So what you see over here is the pole zero map in red for the ARX model. It's a second order system, 2 poles, and there are 2 zeros, probably that there is one also at infinity. The identified output error model in sine has only 1 pole. It's a first order system. Well, a pole zero map is an interesting tool. So assume that you have a situation where you have a pole with its confidence interval over here, and you have a zero that is very close by with its associated, and I will draw it above, confidence interval. In such a situation, you have a near pole zero cancellation, and this is an indication that you could probably use a model structure with fewer parameters. So having lots of near pole zero cancellations in a pole zero map is an indication of overfitting, of using too many parameters in the transfer function you're trying to identify. So this is the Bode diagram of the identified model, and what you have here is the Nyquist frequency pi over ts, and ts is here 0.08 seconds, so this corresponds to, well, approximately 4 radians per second. So as you can see, you have the Bode diagram, and around the Bode diagram you have the 95% confidence interval. So you can have an idea of the accuracy of the model at a given frequency. So you can see here that the accuracy at the very high frequencies close to the Nyquist frequency is not that good, because the confidence interval becomes larger. This means that probably there is less information in the data at this particular frequency that can explain the system. The Bode diagram can also be used in some way to validate models. If you have used, well, different model structures and you obtain models with similar Bode diagrams, this means that, well, you can have confidence in these models. You have obtained 2 similar Bode diagrams with 2 different methods. Well, this concludes this hairdryer example, and if you go through the course for the first time, it's normal that you do not understand all the concepts, because we haven't spoken about input-output dynamics, we haven't talked about noise models, we haven't talked about correlograms, and so on. So please take the time to come back to this example when you have run through the course in its entirety, and also have a look at this example and other examples that are available in MATLAB using the command docident before you attend, well, the system identification laboratory.